So these 4 problems are all about basically the end behavior, as you may recall. On our quiz, most of you did pretty well with this, but a couple of you had a little bit of trouble with it, and those of you who did have trouble with these types, this is a chance for us to get that worked out. So for the first one, in order to know what it's doing at negative infinity, I first need to know the end behavior, specifically the first part of the end behavior. So in order to know that, it's all about this term. That 5x squared is actually totally irrelevant to it, because I'm just looking for the term that has the highest exponent on it. This one is positive, and it is odd. So this is going to have the same end behavior as just a plain old x cubed would have. The 5x squared affects what's happening in between, but it does not affect the ends. And so you can see that this is a down-up. And because it is down and then up, at negative infinity, it's going down. And since it is going down, that means that our answer is negative infinity. All right, let's go sideways from there. Again, I'm looking for a limit at negative infinity, and I want to deal just with the term that has the highest exponent on it, so it's going to be all about this. So I'm looking at a graph that is negative and even. Therefore, I know that the graph would look something like this. Well, notice that is down, down. And so at negative infinity then, I'm looking at that first down, the left side, and we can see then that it is approaching negative infinity because it's heading down. All right, next one, bottom left. Here we're looking at the positive x squared term, and since it is a positive and an even, we know that is an up, up type of situation. And since it is up, up, that means that at infinity it is heading upwards, and so my answer here is infinity. And then for our last one, the highest exponent term is the leading term once again. It usually is, but it isn't always, so you can't depend on it always being that way. You actually got to think it through. And it's negative and odd. Negative and odd means that it's doing an up-down. All right, I'm looking to see what it's doing at a positive infinity. That's where it's heading down, because I'm looking to see what's it doing as it heads to the right. And it's heading down. So therefore, my answer is a negative infinity for that one. Now, the other part that we looked at last week was the rationals. And how do we tell what's happening at infinity when we deal with a rational expression, such as this? And when doing those, we'd say, well, we can just make the graph, and then we can go based on the graph. There's just one potential issue in this case. Can you make this graph? At least by hand, without a calculator or something like that. Could you make this graph? Probably not. I mean, this is a particularly challenging graph, and yet being able to figure out where the limit is as it approaches infinity is actually very easy to do. And it's just a matter of knowing some rules. Since we're talking rules, we're going to be talking notes. Please add this into your math notes. Now, as you've gotten it written down, let's just make sure that we understand kind of what it's saying. You'll notice here that the ax to the n is talking about the top of our fraction. And so that's the numerator. And so when we talk about n, that's the exponent on the top. Just like this m is the exponent on the bottom. So when we take a look at something like here at bullet 1, when we say that n is less than m, we're saying that the biggest exponent on the top is less than the biggest exponent on the bottom. Basically, that's a situation where we could also describe this fraction as like bottom heavy. Whereas if we take a look at our second one here, if n equals m, then we do have a horizontal asymptote. And you can see it's actually at a little bit of a formula there. It's at y equals a over b. So we actually would then calculate that. Now a, again, that's the coefficient in front of that highest exponent term on the top. And the b, that's the coefficient of the highest exponent term on the bottom. And then you notice for our third one right here, if n is greater than m, it has no horizontal asymptote. So if there's no horizontal asymptote, notice this happens when the top exponent is bigger than the bottom exponent. Therefore, that's what we might call a top-heavy fraction. So if our rational expression is top-heavy, then that's that situation. Now, to put it in those terms, it can often be a little bit easier to remember this. So it could also be worth adding this into your notes, which is just a little summary of what it's saying. This is saying the same thing, just in something that maybe is a little bit more intuitive or user-friendly, if you will. So as you take a look at these, notice what it's telling us. Notice asymptote at y equals 0. Asymptote at y equals a over b. Y equals is a horizontal line, which is why I'm not specifying horizontal asymptote, because the equation tells us that this asymptote must be horizontal. And then if it's top-heavy, there is no horizontal asymptote. We saw that up here. But one little detail that I'm giving you here that the notes did not give you up above there is that when you are looking at something that has no horizontal asymptote, you can actually figure out how it's behaving by just treating it like a polynomial of degree n minus m. So like if I have x cubed over x squared, that's the same as x, right? I then just deal with it as, okay, what would the end behavior be of an equation that's just y equals x? And you'll see that in action. We're going to practice that here in a moment. But now one other little detail here is we're talking about the asymptotes. And you've been using asymptotes for a few years now, and you've been seeing the asymptotes come up in various graphs and functions along the way. But our definition of an asymptote was always just kind of generic. We understood what it meant, but it wasn't actually the technical definition. You can only actually get the technical definition of a horizontal asymptote now because we've now done limits. This is the actual definition of a horizontal asymptote. And you'll notice by taking a look at this that the limit as x is approaching infinity could be that, or as it approaches negative infinity. And so what that means is that you can have a horizontal asymptote of a graph that's only on one side and not for the entire graph. And so this graph might be an example of one where you can see actually we could have different horizontal asymptotes. Like on the left-hand side, I can have that horizontal asymptote down there. And on the right-hand side, as we approach a positive infinity, we can have a horizontal asymptote up there. The horizontal asymptotes do not have to approach the same number at negative and positive infinities. You can have a graph that has them in different places. You also could have a graph that just has an asymptote heading off to the left and no asymptote as we go off to the right, or vice versa. So this sort of thing is totally possible. It's just not anything that we've ever really had to deal with before, but yes, it can happen. And now we can actually talk about that now that we know what limits are. All right, enough with notes and enough with technicalities then. Let's take a look at actually applying some of this stuff. So we're going back to this equation that we were looking at earlier. And I just want to start by figuring out where the horizontal asymptote of this equation actually is. All right, now to answer this question about where the horizontal asymptote is, the first thing we do is we think about, is this fraction top-heavy, bottom-heavy, or is it balanced? Well, which is it here? Bottom-heavy. Because I'm only looking at two terms. The one on the top that has the highest exponent and the one on the bottom that has the highest exponent. I'm just looking to see which one's got the bigger exponent on it. And it's the bottom one, right? And so this is bottom heavy. All right, so when we have an equation that is bottom heavy, what do we know about the asymptote? Yep, so to answer that question, we go back to our notes and we see bottom heavy. Okay, bottom heavy says that it's going to be at y equals 0. Nothing else we had to do there. That was all we had to do. And yes, for these types of things, for these rationals, with these rules that we're looking at, these asymptotes are going to be both at negative infinity and positive infinity. It can happen in just one or the other, but those are very specific equations. You're not going to be seeing that in what we're dealing with today. All right, so now that we know where the horizontal asymptote is, please now evaluate this limit. As x is approaching infinity of the same expression, what is the limit? So, in other words, like if I were looking at this graph, it's doing something kind of like this sort of a thing. I'm looking to see what's it doing as it heads out to a positive infinity. Well, it's approaching its asymptote. And where is that asymptote? Zero. So the limit is 0. Because the limit as we approach infinity or negative infinity is the horizontal asymptote, if a horizontal asymptote exists. Having seen what we were just doing there, I'd like us to continue practicing that. So please, for each of these, please identify where is the horizontal asymptote of each of these two equations. And as you might expect, we're then going to use that information to figure out what the limits are. So for the first one here, on the left side, the first question we ask is it top heavy, bottom heavy, or is it balanced? I'm looking at the two terms that have the highest exponents on top and bottom. Notice they're both squared, so this is balanced, yes. And if it's balanced, does it have a horizontal asymptote? Yes, it does. And so it's going to be at y equals, is it y equals 0? Nope. Because this is the one where I actually have to do a little bit of work here. Because I need to take the top coefficient and put it over the bottom coefficient, which of course is 1. So it's going to be 2 over 1, which is just 2. So your asymptote here is at y equals a positive 2. Let's go ahead and grab our other horizontal asymptote, then we'll worry about our limits. So for the second one, over here again, I'm looking at the two terms that have the biggest exponents. So then, is this one top heavy, bottom heavy, or balanced? Top heavy, because the exponent on the top is bigger than the exponent on the bottom. All right, if it is top heavy, does it have a horizontal asymptote? No, it does not. So there is no horizontal asymptote. It does not exist. Now, we will still be able to find the limit though, and we'll take a look at that in a moment. But first, let's go ahead and do this limit. So in this case, since we know that we have an asymptote at y equals 2, the limit as x is approaching negative infinity is going to be approaching that asymptote. And so the answer here is that that limit equals 2. Anytime it has a horizontal asymptote, that's what it's approaching, out at infinity or negative infinity. But in this case, there was no horizontal asymptote. So how do we do it? Well, we treat it like a polynomial of degree n minus m. That's what our notes say. Well, n is the top coefficient. M is the top exponent, and m is the bottom exponent. And so this is going to behave just like an x squared graph. So if I said, what is the limit as x approaches infinity of x squared? What would that be? Well, x squared, we think about our n behavior. It's up, up. And so at a positive infinity then, it's going to be heading upward. So the answer is positive infinity. It reverts back to n behavior knowledge, which is why we started there last week, because you need to know the n behaviors in order to be able to evaluate a rational limit like that. I think we could use a little bit more practice with that idea. So let's go ahead and evaluate this limit, please. All right, so I'm looking at a rational expression, and I assume that you would start by saying, is it top heavy, bottom heavy, or balanced? And this one, as you can see, it is top heavy because our top exponent is bigger than our bottom exponent. And so if it's top heavy, then it has no horizontal asymptote. So then I'm looking at n behavior. Well, to find that n behavior, I would do the 7 minus 5, and I find that this is the same again as like an x squared kind of graph. And so at negative infinity, because our n behavior is up, up, at negative infinity, it is approaching a positive infinity. And that would be our answer there. Now, in this particular case, though, I gave you a particularly simple rational expression because you actually could have figured this one out before this. I didn't even need to give you the top heavy, bottom heavy balance stuff for this particular one because you actually could just simplify this, right? And you could see that that would equal the same thing as 1/3 x squared. Did the 1/3 change the end behavior? No. So still, as I was heading left, I was still heading up. And so it was still infinity. A little side note on this. What if it was negative 6x to the 7th and over 18x to the 5th? Would that change our answer down here? Yes, it would. Because that would be the same as negative 1/3 x squared. That's a down-down end behavior. So you do need to actually look at the numbers that are involved, because that would have made it a negative infinity in that case. Okay? Now, of course, we need to know these rules because they don't all simplify quite as nicely. I wouldn't want to try to be simplifying this, but we can use the rule to answer it. So please, take a moment, evaluate this limit. All right, so in order to answer it, first of all, is this top heavy, bottom heavy, or balanced? Yep, it's top heavy because the 5th is more than the 3rd. All right, so that tells me then I got to think about end behavior. So really, I'm just thinking about what would it be if I had like 12x to the 5th over 2x cubed. It's going to have the same end behavior as that would. So it's going to have the same end behavior as 6x squared. A lot of x squareds here, right? All right, so the end behavior of that would be up, up. And since this would be up, up, at negative infinity, it would be heading up. So that means that it's approaching a positive infinity as our y value. All right, another one to practice. Last one we're going to do just like this. All right, now this one I hope took longer to write down than it did to actually do. Is this one top heavy, bottom heavy, or balanced? Bottom heavy. And every single time that it's bottom heavy, our asymptote, it does exist and is always at 0. And so, as this approaches infinity, it is approaching 0. By the way, remember, the whole thing about the like bottom heavy, top heavy, and all that stuff dealing with asymptotes, it all comes down to it being at infinity or negative infinity. If this was a number here, we'd actually have to go different routes. Because remember, this only works as we're taking a look at out to infinity. Wait, you mean I don't just look at that first term? Oh. Yeah. Notice on the top, it's an 8. And on the bottom, it's a 6. Remember, we can't just look at the first term. And so, that means actually, I guess we're actually going to have to put in a little bit of thought, right? It's actually negative 3x to the 8th over 10x to the 6th. That's really what we're dealing with then. Oh, so maybe it's not 0 then, huh? Well, that would be the same as negative 3/10 x squared. It's going to have the same end behavior as that. This other stuff, it doesn't change the end behavior. It changes the way the graph looks, but it doesn't change the end behavior. So then, what's the end behavior of negative 3/10 x squared? Down, down. And so then, as I'm approaching a positive infinity, I'm heading downward. And so it's actually negative infinity. Good. Having done those, I figure if you can do it one way, you can do it the other way. So these are 4 separate problems. These are not describing the same f of x function. This is describing 4 separate f of x functions. So please write a function f of x that would meet the requirements that you see shown here for each of them.